Hey there, Math 398 fans. Going to continue my little tour of these projects. So here is the surface area. In our calculus series, we don't include surface area as one of the topics. It's just for time. But that doesn't mean we can't have a project to explore it. So I do surface area, but in the setting of volumes of revolution. So this would be for a Math 125 course. But what's interesting to me, something I've thought about recently, is how it relates to what are called minimal surfaces. Now, this is a higher level math topic, but I think I was able to write a project that allows you to get right to the edge of that research. And so I think that's what makes this interesting. So I basically recap. Here's the equation for surface area. You can do it in terms of x or in terms of y, and that we're just going to explore this a little bit. So I think that's kind of interesting in itself. Whenever I get a new formula, I want to test it out. And so I'm going to have students find the volume of the cone, the surface area of the cone, the surface area of the sphere, and then I'm going to have them go through the following question, which I'll present here. So first, I'll show you this. So, and I'll have visuals. You know, if anybody solves these questions or comes up with an interesting new one, I will show this. So those are the surface areas, blah, blah, blah. We'll find those, no problem. Now, it may lead to an integral we can't do, which is part of the reason. So I'm going to have students do a numerical integration. They'll set it up. They'll see that it gives what you expect. I always like to start any new project with that. So the question I wanted to ask, which I was glad that this sort of overlaps with it, is imagine you have two rings equally apart. What is the smallest surface area that connects those? So that's a much bigger, higher powered question, I would say. So what can I say about it? Sorry, get my fat head out of the way. Okay, so here we go. It would seem that maybe just doing this would be minimal because a straight line is the shortest path between 2 points. That's true. Is that the minimum surface area? Well, we can compute that, no problem. It turns out that's not the minimum surface area. You're able to touch every point on both of those circles with a different surface that's completely connected, no holes or anything, besides the one in the middle, but that has minimal surface area. It turns out if you dip both those rings in soap bubbles and slowly pull them apart, it forms this minimal surface, which is called a cantenoid. I've been thinking about this, and I know that it's a hard subject in math, but I thought students don't have to understand it to compute it. So I numerically figured out what this was, and I give it in the project, and I have students compute the surface area of both those things. They're both surface areas of revolution. So our formula works. You'll need an integrator to do it, but I thought that's kind of interesting, and you'll verify that the surface area of the blue is smaller. So I think that's kind of an interesting little intro to this idea of minimal surfaces, which is a fascinating area of mathematics. So there you go. I also think that it would be easy to ask other surface area questions. Go out and find some shape that's a revolution and find its surface area.